Today we will learn how to measure visual acuity, means our perfectness of vision, or how distinctly we can identify very small objects, or that is measured. This is called visual acuity, how distinctly we can identify very small objects, and we can know its contours, we can know all the intricate things about, and the thing doesn't get blurred. That is a measure of our visual acuity. And visual acuity is measured by this help of the chart called Snellen's chart. Snellen's chart. And what is this Snellen's chart? This Snellen's chart contains letters called optotypes. These letters are very significant. It has a real importance, and these letters are in such a way that these letters have particular characteristics. And these letters should be read from a particular distance, and then only we can say that we can measure visual acuity through this. Now, what is the basic principle? What is the basic principle of this optometry and this measurement of visual acuity? The basic principle is that why we read some letters from a particular distance. If we can read that letter, if you can read a letter and go somewhere below, the letter sizes are diminishing as we read this Snellen's chart from top to bottom. And while these letter sizes are diminishing at a particular line, say this line, we stop. Say this line, we stop. So we can read up to this line, and we cannot go further. Here the letters are getting hazy, these letters are getting obscured, and we can't tell what are these letters. So we do it by this line. We tell that, okay, from this line we get a particular information, and say that your vision is this by this, and this by this is actually a fraction. It is called Snellen fraction. And what is this fraction? What is this ratio? This ratio is devised by a somewhat a rule, and I'll explain you this rule now. Now, if somebody I have to say that somebody reads this letter from a particular distance. Now, this distance is, I say for an example, I fix up this distance. Say this letter is read from a 6 meter distance from the eye. The subject is sitting here, and this letter is read at a 6 meter distance from this subject. Now, while he reads these letters from 6 meter distance, he reads this line, the next line, third line, the fourth line, and say he stops at this line, fifth line. So if he stops this at this fifth line, then what information do we get when he stops at this fifth line? That is very important. Now I'll explain you about this importance. How do we then calculate the visual acuity from this information? Now, this is done because the subject is sitting at a 6 meter distance, and these letters have particular values. All these letters have particular values. All these letters have particular values. And what is this value? These letters are called optotypes. Optotypes. Why? Because each of these optotypes are, the size of each of these optotypes are made in such a way that these are particular distance optotypes. Means that if E is a 60 meter distance optotype, E is a 60 meter distance optotype. That means if you read E, a normal person, if reads E, he can read E from 60 meters. So it is a 60 meter distance optotype. Say this line is a somewhat lower than 60 meters. Say this line is a 50-meter distance optotype. This line is a 40-meter distance optotype. We can express these things in feet also. So 60 meter comes to around 200 feet. This comes to around say 100 feet. This comes to around say 70 feet. So this is the 200 feet of optotype. This is a 100 feet optotype. This is a 70 feet optotype. Likewise, this the fourth line, this fourth line is the 50 feet optotype. So the first E is the 200 feet optotype. The second line is the 100 feet optotype. The third line is a 70 feet optotype. So likewise, these are particular feet optotypes, means that normal eye should read this letter at 200 feet, should read the second line at 100 feet, should read the third line at 70 feet. So but you're not reading this E at 200 feet away. A normal eye can read it at 200 feet away, but you are sitting at around say 6 meter distance. So 6 meters is equal to 20 feet. So you are just 20 feet apart from this line. And even then, if you can't read a 200 feet optotype, a 200 feet letter, which a normal eye can see at 200 feet, so your visual acuity is 20 by 200. That means if you stop at say 1, 2, 3, 4, fourth line, so this fourth line, if you stop here, if you stop in these optotypes, so this is the fourth line. So you should read this 50 feet optotype, because these sizes are such that a normal eye can read this optotype from 50 feet, but you are sitting at 20 feet, so you should read it, but you could not read it. So your visual acuity is 20 by 50. So it's a fraction of 20 by 50 is a fraction which is less than 1. So your visual acuity has decreased. Your visual acuity has decreased by from 1. It's now a fraction of 1, 20 by 50. If it is 20 by 70, it is still lower. If it is 20 by 100, it is actually 0.5. Your visual acuity has lessened by half. So you can see half that a normal eye can see. And we say that if it is 20 by 200, it is actually a blind eye, that more or less this eye cannot see anything. So what is the normal? When a subject sitting at 20 feet will see a 20 feet optotype. A 20 feet optotype is present in the 8th line. 1, 2, 3, 4, 5, 6, 7, 8. So if we can read this optotype clearly, so we say that okay, it is a 20/20 or a 6 meter by 6 meter vision. 20 feet is equal to 6 meter by 6 meter. So the visual acuity is 1. It can be even greater than 1. Normally our eyes for normal person has visual acuities of greater than 1, 1.5, it can be even 2. And as there are defects in the refractive defects, say we have myopia or we have nearsightedness, so that is called myopia. We can only see near things when we cannot see things which are far away from. So that is called nearsightedness or myopia. In those cases, this visual acuity for the distant objects gets lowered and we cannot see that. So we need to take some lenses so that our vision gets corrected. And by and by the Snellen's chart, by reading the Snellen's chart, we get an approximate idea about how much the vision is lowered. Now I will tell you about this optotype. This optotype, basically, why it is called an optotype? Because this letter has subtended an angle. This letter has subtended an angle of 5 minutes radian in the retina. 5-minute radian arc in the retina. So this angle of 5-minute radian arc, 5-minute radian arc in the retina. In this retina, here we have the retina. If this optotype has subtended an angle of 5-minute radian arc in the retina, then only this retina can see, we can distinguish this object, we can distinguish this optotype, and we can process that image in such a way that we can clearly see that image. A 5-minute radian arc is absolutely necessary for an optotype to subtend on the retina. So if this is a 200 feet optotype, so this optotype, this largest letter of this Snellen's chart should, this largest letter of the Snellen's chart should subtend an angle of 5-minute radian arc in the retina when the subject is, because it's a 200 feet optotype, the subject is sitting 200 feet away. Similarly, optotype which is say 20 foot optotype, this last line is a 20 feet optotype. So this optotype, this particular letters, say here is another E, a very small e, this optotype will subtend an angle of 5 radian arcs in a subject's eye who is 20 feet away. So both these letters will subtend and have to subtend an angle of 5 radian arcs. Both of this has to subtend an angle of 5 radian arc. For here the subject can sit at 200 feet away, still the angle is a 5 radian arc angle. Here the subject is sitting at 20 feet away, and here also the angle in the retina is 5 radian arcs. So the height of these letters, this height of these letters is actually 68.7. If we multiply, if these letters have particular sizes, so this is, you have to remember this number 8.73. This 8.73 is actually the size of this 8th line. 8th line letter, 8.73 millimeters. So 8.73 into this factor, the factor is constant, 68.76. So it is around, say, 70. I approximately say it as 70. And this as 9. So 9 into 7 is equal to 9 sevens are 63. So it is around 6 meters. It should be around, the distance should be 6 meters. So if this letter is 10 times the size, if it is 87.3, so 87.3 means, say, 90 millimeter. 90 millimeter into 70, 9 sevens are 63, 6300. So this should be around, say, 60 meters. 60 meters away. So the distance, the optotype size should be 68 times the optotype size. This optotype size is governed by certain factors. The optotype size, the size of the optotype should be 68.76 times the distance. And this, so the optotype has a particular size. By now we have understood that the optotype has a particular size, and this optotype is divided into 5 fractions. Each fraction is subtending an angle of 1 radian minutes in the retina. And by this Snellen's chart, we actually calculate a fraction called Snellen's fraction and tell whether an eye has a diminished vision. Is there any reduction in the vision? Is there any reduction in the visual acuity? And we do it by the visual acuity, by this formula. Visual acuity is given by distance at which the test is done, that is 20 feet. The distance at which the test is done is a numerator, so it is 20 feet. And the distance of the identified optotype, if the subject can identify it up to here, so distance of the identified optotype, if it is the fourth line, so it is 50 meter. Distance of the identified optotype, this is a 50 meter optotype. A 50 meter optotype means a normal eye should see this optotype, this fourth line, from 50 meters. But so distance of the identified optotype which subtends an angle of 5 arc minutes, which subtends an angle of 5 arc minutes. So in this fourth line, these optotypes will subtend an angle of 5 radian arc minutes in the eye when the subject is standing at 50 feet away from the letters, and he can read up to this line. So the visual acuity is 20 because he was standing at 20. Distance at which the test is done is 20 feet, and now he could not read what he should have read from 50 feet. He should have read that from 50 feet, but he is not being able to read this optotype, this fourth line optotype. So this 50 is actually what he should have read if his eye was normal. So the reduction, the fraction is 20 by 50, which is lesser than 1. So there is a reduction in vision. Now I'll quickly revise you the whole thing, and I'll go into details of the optotypes and how this, or the character of the optotypes. So if this is a optotype and it subtends an angle of 5 radian arcs, so it has 5 components, 1, 2, 3, 4, 5. The darker is the lines, the dark portions, and the gaps. So the gaps are equal to the line width. The gap width is equal to the line width. So if the gap width is equal to the line width, so there are 5 equal portions of this optotype, of this E, and each of these equal portions will subtend an angle of 1 minute radian in the retina, because the whole thing has to subtend an angle of 5 radian arcs in the retina. So the height is equal, the height of the height is equal to the width, so it's a square one. This optotype is actually a square, and the letter size is 5 times the thickness of the line. The letter size, the whole size of the letter, the height and width is equal to the 5 times the thickness of this line. It is 5 times, the letter size is the 5 times the thickness of this line. Now there is a formula. Of how do we devise the size of this optotype. So it is actually in such a way that the formula is the height or width of the optotype is equal to 2d tan theta by 2. And what is theta by 2? The theta by 2, theta is this 5 minute arc. is this 5-minute arc. And what is this D? This D is the distance from the optotype, and this distance from the optotype is governed, it has a relation with this size of the optotype. The size of the optotype, the size, what if the size is say X, the distance has to be 68.76 the size of the optotype. So the optotypes, if we say that a optotype is of size 8.73 millimeter, the distance should be, it has a relation, the distance should be 68.76 into 8.73, 68.76 times the size of the optotype, and then this multiplied by this, then the angle that this optotype subtends on the retina will be 5 radian arcs. So it is given by this formula, the size of the optotype, the size or height or width of the optotype, or actually the size of the optotype is equal to 2d tan theta by 2, where theta is 5 radian minutes and distance is actually the size of the optotype multiplied by 68.76. 68.76 is the factor of the distance factor. The 68.76 multiplied the size of the optotype. So if it is 68.7 times, it means say 68.7 times 7 times is approximately, I say it's 70, and this is 8.73, I approximate it as 9. So 9 into 7 is equal to around say 630. That means it is around 600 millimeters. So the distance should be 600 millimeters away. The distance from the Snellen's chart to the eye should be 600 millimeters away. So by this, and that will, and by staying apart by 600 millimeter, the eye in the optotype will subtend an angle of 5 radian minutes. 5 radian minutes. And if a subject cannot read optotype, if a subject stops at a line, and we need to, by definition, this line is an optotype of a particular normal eyed vision. This, if it stops at line 4, and the line 4 is a 40 feet optotype, so the subject cannot read a 40 feet optotype sitting at 20 feet. So sitting at 20 feet, the subject cannot read a 40 feet optotype. So the Snellen fraction is 20 by 40. The 40 here says that he should read this fourth line from a 40 foot distance, but he is sitting at 20 feet distance and still cannot read a line which he should have read from a 40 foot distance. So the fraction is 20 by 40, or his vision is now 1 by 2. So it's a fraction 1 by 2 is equal to 0.5, which is that his visual acuity is only half of that of a normal eye. If somebody cannot read the letter which he should have read at 30 feet, sitting at 20 feet, so this 20 by 30 is 0.6. So he has a lesser visual acuity than 1. It has diminished by 60. If a subject can read he is standing at 20 and he can read a 20 feet letter, so his visual acuity is at 20 feet optotype. He is reading a 20 feet optotype at 20 feet. A 20 feet optotype is in the 8th line, say, and he can now read the 8th line also, because that is the 8th line is the 20 feet optotype, and he can read it sitting at a 20. So his vision is 1. So if we can't go up to that certain line which tells our visual acuity as 20 by 20, 6 by 6, like these fractions which are where the numerator and the denominator is equal, so and the ratio becomes 1, so we'll say that if we can't go to that line, we say that our visual acuity has diminished. Now generally the letters which are used in the original Snellen's charts are C, D, E, F, L, O, P, T, Z. So they're according to BS 2003 standards. These CDEs are kept, and these F, L, O, P, T, Z are replaced by H, K, N, P, R, U, V, Z. Z retains, Z is retained, T goes away, P is retained, this T goes away, and new things come here. R comes, U comes, H comes, K comes, N comes. So these are the according to 2003 standards. Now just quickly, if I revise it, and a little bit thing is also is that I have alternatively used 20 feet and 6 meters. 20 feet and 6 meters. 20 feet is equal to 6 meters, because we know that 1 feet is around 30.48 centimeters. 30.48 centimeters, and if 1 feet is 30.48 centimeters, so if we say 20 feet, so 20 into 30.48, which is equal to 20 into 30 is equal to 600 centimeters, which is around 6 meters. So 20 feet is around is 600 centimeters or 6 meters. So I can reversibly use 20 or 6 here. If we can write the Snellen's fraction as 6 by 6, when we say it as meters, we can write it by 20 by 20. And the first optotype, which is the largest optotype, it is a 60 meter optotype or a 200 feet optotype. That means you should read this optotype. A normal eye reads this optotype staying 60 meters away from this optotype or 200 feet away from this optotype. And if he sits at 6 meters, he will obviously see it very clear and loud and very clearly, because it is subtending an angle of around, say, 10 times more. It is subtending an angle of 50 radian arcs. So it's a huge portion of retina is stimulated. If it's a very small portion of retina is stimulated, then only the problem of visual acuity comes. If a small, the distance in the retina in the fovea centralis, a very small neurons are stimulated. Here a large subtending angle will stimulate a larger area of retina, and that will make the object clear and loud. But if it visual acuity is based on that this optotype will have to subtend an angle of 5 radian arcs in the retina, and by seeing E, the largest one from 200 feet, or the 8th line smallest one from 20 feet, we can see both at this largest one from 200 feet and the smallest one which is the 20 feet optotype from 20 feet. Both subtends an angle of 5 radian arcs in the retina. and this 5 radian arc will be divided between the characters of the optotype 1, 2, 3, 4, 5. These 5 portions will be subtending an angle of 1 radian arcs each, and then we can distinguish this optotype in the retina. So this is the minimal distance, 1 radian arc for this character, that for this character to get distinguished in the retina. 1 radian arc is that minimal distance for that character to get distinguished in the retina as a different line. And there comes the question of visual acuity, which we measure by this Snellen's chart, which has these optotypes arranged from the largest one is in the top, and the smaller optotypes comes below, and we read up to a certain line. When we can't go beyond that line, we say that we have read this optotype line, and this optotype line is a particular foot away optotype line. Say it's a 40 feet away optotype line or a 30 feet away optotype line. If it is a 30 feet away optotype line, then that I should have read it from 20 feet, because it's a 30 feet away optotype line. A normal eye reads that optotype from 30 feet. The normal eye reads that optotype from 30 feet, which I cannot read at 20 feet. So I have a defect. And what is the defect? It is 20. I am sitting at 20. So it is 20 by 30, because I am not being able to read a optotype which I should have read at 20, and which is a 30 feet optotype. A normal eye can read at 30 feet. That optotype, the normal eye can read at 30 feet, which I cannot read even at 20 feet. Even at 20 feet, I cannot read a 30 feet optotype. So the visual acuity is 20 by 30. So you can you can use this Snellen's fraction as by this sentence, that even if this is the Snellen's fraction, big D by small d, you can read it like this. Even at a particular, this small d is what you will read this small d as, even standing at 20 feet, I cannot read a 30 feet optotype. Even standing at 20 feet, I cannot read a 30 feet optotype or a 40 feet optotype, which I should have read, because a normal eye reads it optotype at 30 feet or 40 feet. So according to that, if I cannot read a 40 feet optotype, my vision is 120 by 40 or half. If I cannot read a 30 feet optotype, my vision is 20 by 30, that is 0.6. If I cannot read a, say, 70 feet optotype, my vision is 20 by 70, that is 2 by 7, which is still lesser fraction. If I cannot read a 200 feet optotype, and then I am virtually blind, because 20 by 200 is 1/10. My vision has gone down to 1/10 of a normal eye. Thank you for listening to me. Goodbye.